So vector.
Yes, we're going to talk about the next subject with vectors. Okay, or start the next subject with vectors. We kind of got a little off track, so if you notice, I think last night there was homework in Canvas. I have ended up shifting things around, so and I'm also shifting our next test, or our last test before the exam. It's not going to be this Thursday anymore. I'm going to shift it to next Tuesday. Okay. Tuesday should be fine. It shouldn't be that hard of a test. We should get it done in a period. I should be able to get it back to you by, because there's no test in the AP Calculus doesn't have any more tests until basically their exam. So they should be done with the grade and then get it back to you. Okay. I think I graded your other tests. Those of you who finished them. I need to give them back to you. The grades are on Canvas. I didn't figure out where I put them, but they are graded, so I'll get those back to you tomorrow. Okay. And we're going to spend, after the test Tuesday next week, we'll spend Wednesday, Thursday, and Saturday reviewing for our exam. Okay. And so look to Canvas to see about review times and things like that, because that's where you're going to find all that info. Got it, everybody?
Sure.
All right. So,
You said next week?
I'm sorry?
Next week or
Next Tuesday.
Next Tuesday, yeah. Okay, that's our last regular test. Okay. All right. What we're going to talk about today, okay, is we're going to learn a new operation that's specifically for vectors. It's called the dot product. Okay. It's a form of vector multiplication, okay, but it's different than a scalar multiplication. And it works specifically for vectors. The other thing about the dot product is some of the standard rules of vector multiplication don't necessarily work perfectly for it. So you do want to pay attention to how it works, okay? The actual process of the dot product is fairly easy. Basically, if I have two vectors given vectors u equaling u1, u2, not to be confused with the band, and v being v1, v2, not to be confused with the missiles, then u dot product v, okay, is equal to u1 times v1 plus u2 times v2. Okay? So that's how it is. Now, this is the dot product. Okay? So, basically, note here, I want to be very careful with the notation here, okay? Dot product, okay, actually uses the multiplication dot. So if you're dealing with vectors and you see the dot in between two vectors, that's specifically saying do a dot product. You're not going to see this done with the X symbol for multiplication, because that's a different type of vector multiplication called cross product. Okay? Oh, wow. We are not learning cross product at this time. In fact, I don't think we're ever going to get to cross product. Okay? Its applications are different from what we're going to be doing. Okay? But do keep that in mind that there are basically three different forms of multiplications when it comes to vectors. You got regular scalar multiplication, that's easy. You got dot product, easy, and you've got cross product, which is also fairly easy to do. It's just that you want to make sure you keep track of what each of the symbols means. Yes?
So if the dot would be omitted and it's a UV, would that still be the same?
Technically would not be a dot product then.
Oh, okay, that would just be a combined vector. No?
That would be poor notation for whatever you're trying to say. Ooh. You wouldn't write vectors that way.
Oh, okay.
Okay. To write them UV. Okay.
Yeah.
So do keep that in mind. Okay.
Yes, sir.
But this is how the dot product works. Okay. Let's do a quick example, and then we'll go over some of the basic basic properties. Okay. So an example here, let's let u be equal to the vector 2, 5, and v is going to be equal to the vector 3 minus 1. Okay, then u dot product v is going to be equal to 2 times 3 plus 5 times minus 1, which would be 6 minus 5, or 1. Okay? And so that would be the dot product of these two vectors. Okay. Any questions about how that's done? It's a fairly simple operation. It's just a matter of knowing how the operation works.
So the
Okay. Dot product by itself, kind of what it represents, it's a little weird what it actually represents. It's sort of, it's basically figuring out a, not magnitude, but sort of a, you can use it to find magnitude, but what it's really figuring out here is sort of like a directed, I don't know what's the proper word for it. It's sort of taking the two vectors and combining them into just a single number. Okay, and we're going to learn later on. Actually, I believe we're going to cover matrices in the spring. When we do, you'll see this operation done there. Or an operation very similar to what we're doing with matrices, called the determinant, and it's basically taking everything and boiling it down to one number. You can think of matrices as being a collection of vectors, in which case you're boiling it all down to a single number. Okay, so that's sort of what's going on here.
But the number is a scalar, right? No direction.
Yes, it's a scalar. It's not a new vector. Everyone got that? So when you do the dot product of a vector, you're not finding a vector. You're finding a scalar. You're finding a constant number. Okay. The other thing is the dot product of two vectors has a lot of uses. Okay, and so we're going to learn a few of those uses but as we move forward. But any questions about how this operationally works? It's fairly straightforward, right? Okay. All right. So some properties of the dot product. Okay. Okay. First property is the dot product is commutative. Okay, meaning that if I do the dot product of two vectors, so u dot v is actually equal to v dot u. Nice and useful. Okay, that's nice.
Commutative, right? No?
Yeah, that's commutativity. Okay, it is not associative. Okay, which is something kind of interesting. And if you actually sit down and write out why it's not associative, it makes perfect sense.
What would associative mean?
Grouping with parentheses.
Okay.
So if I had three vectors, u, v, and w, u dot product v in parentheses, okay, dot product w actually makes no sense.
Okay.
Because the u dot product v would be a scalar at that point, and you can't do a scalar dot product of vector. That doesn't
give you a
work.
scalar.
Okay, so that associative property doesn't really work for these things. Okay. Next one is if I take the 0 vector and dot product it with anything, I get the constant number 0. And I'm going to make a note here that it says 0 as a constant. Okay. And this is right here, 0 as a vector. Fairly straightforward. Obviously, if I times a bunch of things by 0, it all comes out to be 0. Okay.
Yeah.
Now, the dot product does preserve distribution. Okay. So I have vector u dot product with the sum of vectors v plus w. Okay. The end result is the dot product of u and v plus the dot product of u and w. Okay. So while it's not associative, it does have the distribution property. Okay. Which is nice. Okay. All right. Next up, if you do a dot product of a vector with itself, you get, what do you think you're going to get? The magnitude squared. Because they're essentially doing the Pythagorean theorem to it, v1 squared plus v2 squared, but you're not taking the square root of it. Okay, so it'd be the magnitude squared. Okay. Go on.
So wait, is this two vectors dotted together, or two dot products together?
So a vector
Yeah,
doing
a
a dot
simple
product
vector.
of the vector with itself.
Perfect,
So
I got it.
v dot product v. Okay,
Yeah.
so it's one dot product, but it's the same vector in both. Okay.
Yes.
And interestingly, okay, if you have a scalar times the dot product of two vectors, okay, that scalar, you multiply it first, okay, to one of the two vectors. It doesn't matter which one you do it to. So it would be scalar times u dot product v, or u dot product scalar v. Okay, but you do that first before you do the dot product. Okay. Any questions there?
What's the C there? I'm sorry.
Constant. C for constant. Okay, so I'll add that down here in the middle. C is a constant scalar. Okay. All right. And so that is basically everything there is to know about the dot product. Okay. It is fairly straightforward.
How would that show up on a test? Would you just be testing us directly on that, or what?
No, I mean, I would just have problems saying find the dot product
Okay.
of
yeah.
two vectors, and I might throw something in here that can be a property, and if you organize the property, you can quickly figure out the answer. But I mean, to be honest with you too, a lot of times when you see the properties of something, it's more of just so you know so you can know what they are, so it can help you when you're doing the mechanical part of it. I mean, to be honest with you, if you didn't know any of this, okay, you could still, you'd still be able, as long as you know what the dot product was, you should still be able to figure out all this,
Right.
even without knowing the rules specifically. Okay, sort of the same reason. It's basically letting you know things you can do and things you can't do. Okay. Yeah. All right. Any questions there? How that works? All right. Make sure you got this list down. Does everyone have it down? Before I move on. Okay. It's also in the book, so always stick it there. All right. The next, now, the dot product by itself, it's kind of a nice little operation, not hard to do. One of the reasons why the dot product exists is because it allows us to do a bunch of different things, okay, with it, making it so that way we can do some work with vectors and stuff. So let's now look at some of the uses of the dot product. Okay. The first use we're going to use the dot product for is find the angle between two vectors. Okay. This is something that if you looked at the homework prior to me changing it, you'd be like, well, how does that work? Because there's some homework problems from last night's work that had this, but we hadn't gone over it yet, so want to go over it. Okay, find the angle between two vectors. Turns out the angle between two vectors, okay, is written by the following formula. It's the cosine of whatever the angle is, okay, is equal to the dot product of the vectors over their magnitudes multiplied together. Okay, So if I have two vectors u and v, okay, the dot product of u and v divided by the magnitude of u times the magnitude of v is equal to the cosine of the vector. Okay.
So arc cosine.
Or the cosine of the angle between them. And this is actually one you could show by, if you drew out a triangle, all right, basically if you draw out any triangle and use the vectors as two of the legs of the triangle, you could easily show that this would end up being the case. Okay, it doesn't take, not particularly difficult to do. We don't have to worry about ever proving any of these rules, but this is one you could, anybody in the class can actually prove with just, pen and paper in like 5 minutes worth of time. It's not hard to do. Okay, but that's the formula for it. Okay, so what we're going to do, basically, this allows us to figure out kind of the relationships here. Let's go through and take a look at an example of this. Okay, so let's find the angle. Between vectors 2, 5, and we'll do 3 minus 1. Okay, those are my two vectors. Okay, so what I need to do is the dot product of the vectors divided by the product of their magnitudes. Okay, so first thing I need to do is figure out what u dot v is. Okay. That should be easy enough. How would that be written?
2 plus 5
Okay.
times 3
So
plus
2 times
5
3
plus
plus 5 times
negative
minus 1. Okay? Which would be 6 minus 5 or 1. We actually did that example earlier. Okay? Alright. And then next up is the magnitude of the two vectors. So what's the magnitude of u going to be? Anybody know? How would I find it?
2 squared. 2 squared. Oh, yeah. Isn't it 2 squared?
2 squared plus 5 squared, and then what?
Square root.
Take the square root. So it's the square root of 29, basically, is what it is. Okay.
Why is it 2 squared and that?
Okay, so vector u is 2, 5,
Okay.
okay? And you find magnitude by basically applying the Pythagorean theorem to it.
Okay,
Okay?
you're saying find the magnitude. Okay, got it.
Yeah. Okay, so, 2 squared plus 5 squared, 4 plus 25. Okay, and then you take the square root, which is 29. How about the magnitude of v?
Root 10.
Root 10. Good, whoever said root 10. Because it's 3 squared plus negative 1 squared, that's 10. You take the square root of it. Okay? So root 10. Okay? Alright, so now, to find the angle between them, now we have all the information we need. Okay? To find the angle between them, we just simply set this up as the cosine of theta is going to be equal to 1 divided by root 29 times root 10, which by the way is 1 over root 290. Okay? So cosine of theta is equal to 1 over root 290. I'm going to take the arc cosine of both sides. That gets me theta by itself. So theta is equal to the arc cosine of 1 over root 290. At this point, you will need a calculator. Because I don't know about you, but I don't know what the square root of 290 is off the top of my head. Okay. I do know it's not a nice number. Okay. Make sure I'm in degrees. I am. Arc cosine of 1 divided by root 290. And I get an 86 degree angle. Okay. So it's 86.634.
So minus these.
Yeah. 4 degrees. Stupid dead spot. Alright. Good. Alright. So, any questions on how this process works? It's a little cumbersome because there's a lot of little things that you have to do. But none of them are really that difficult to do. To be honest with you, this is really a formula, so you're just finding the pieces and sticking them in like you would a quadratic equation, or quadratic formula, a squared plus b, minus b plus or minus yada yada yada. Okay. Also, too, I'm not very keen on having you guys memorize something like this. So on a test or a quiz, I would probably just give it to you, to be honest with you. Because there's more important things I would like you to memorize, like law of cosines, something like that. Okay. Dis, not so much. Okay. So you know how it works, but you don't necessarily need to be like, remember in your head this exact process. Although it's not a hard formula, it's a very simple one. Okay. But you can figure things out. Okay. All right. Any questions on how any of this works? Okay. And that's a fairly straightforward example. Okay. But what this allows us to do is figure out the relationship between two vectors as far as their angle is concerned. Okay. Here we got the angle to be 86.34 degrees. Okay. This allows us then to go through and talk about the various ways we can classify vectors. And it turns out we do indeed talk about two vectors with their angles in relation to one another. Okay? If the angle between two vectors is 180 degrees or pi in radians, okay? Vectors u and v are opposites. Are in opposite directions. I should say they're directly opposites. But they're in opposite directions. Why would that be the case? What's 180 degrees look like? It's a what? Straight line. Okay? So this would literally be a system like that right there. Okay? Alright. Some of these are rather silly. For example, if they make a if they make an obtuse angle, we would say they're obtuse. If they make an acute angle, we'd say they're acute. Okay? So I'll write those up. But so theta is, let's write this up properly. If 180 is greater than theta, which is greater than 90, or pi is greater than theta, which is greater than pi over 2, u and v are obtuse. Okay. 3, if 90 is greater than theta, which is greater than 0, or pi over 2 is greater than theta, which is greater than 0. Okay. U and V are acute. Okay. If theta is equal to 0, U and V are in the same direction. Right? They'd overlap one another. Alright, and here's the last one. Okay, which one have I left off so far? I did 180 degrees, less than 180 degrees, but greater than 90, and not 360.
Larger than 180.
Okay.
All 90% just be negative.
Yeah, it just goes flips around. Okay.
What about 0?
We just did 0. Let's scroll up a little bit.
Yeah.
Maybe you can see it. Which one are we missing?
Wait.
Nope.
90 degrees.
90 degrees. I left off 90 degrees.
Oh, yes.
Okay. I said 180 or opposite directions. 180 between 180 and 90, they're obtuse. Between 90 and 0, they're acute. 0 in the same direction. But what if they're at 90 degrees of each other? Okay. I left that one off because it ends up that relationship is special. Okay, so in theta is equal to 90 degrees or pi over 2 if we're in radians. Okay, vectors u and v are orthogonal. Okay, orthogonal is basically a synonym to is basically a synonym of orthogonal is basically synonymous to perpendicular. The difference is perpendicular implies that you actually have two line segments. However, you do not require there to actually be a vector to be orthogonal. For example, if one of the two vectors was the zero vector, which is just a single point on the graph, the zero vector is technically orthogonal to every other vector. Okay, because if you and so that ends up kind of making things a little different. So it's this word orthogonal, and two vectors are always orthogonal if their dot product is 0. Okay, so if I took the dot product of two vectors and got 0, that means the vectors are orthogonal. That means they really lie at right angles to each other. Okay, and so it ends up being a kind of important distinction. How do we know they'd be at right angles if their dot product is 0? What would that mean for the cosine of the vector, or the cosine of theta, or the arc? Basically, what's the cosine of 90 degrees equal to? 0. So if we applied the find the angle between two vectors formula, it'd be cosine of theta is equal to 0 over, doesn't matter.
Yeah.
Okay? In which case it would be 0. The only one in which case that would be problematic would be if you're doing the angle between a vector and the 0 vector. But when you think about it, it should be problematic because a 0 vector is what? There's nothing there, right?
Yeah.
So the angle between it would be there's not really anything there to make an angle between. But you could always argue, well, that's considered to be orthogonal, therefore the angle between a 0 vector and any other vector is 90 degrees. Always. Hey, math don't lie. Them's the rules. So you could always make things up that way. All right, any questions there? All right, let's take a look at an example, how to determine, basically, for all those other ones there, okay, opposite directions, obtuse, acute, same direction, you're really just, basically, you would actually have to go throughout the whole formula. Dot products aren't going to help you. However, they do help you. Well, I mean, they help you because you use the dot product to find the thing, but there's no quick way to do it. Dot product does tell you quickly if they're orthogonal or not, because again, if the dot product is 0, you know they're set. So that's kind of a way to quickly figure out a relationship between two vectors. You do the dot product. If it's 0, you know they're orthogonal. If it's not 0, you know then they're going to fall into one of these other systems. Okay? And so it's just a matter of which one they fall into. Okay? And actually, you can take that a step further. Okay? If the dot product of two vectors is a positive number, okay, the vector is going to be between 0 and 90 degrees. If the dot product between the two vectors is a negative number, you know it's going to be between 90 degrees and 180 degrees. Okay? I can write that up if you want to as a little rule.
So
Okay?
wait,
So
the
kind of
first
quick-
quadrant or the third?
Sorry?
The first quadrant or the
Yeah, second quadrant, basically.
Oh.
So, kind of like relationship between angles and dot products. So, first one, if u dot product v is greater than 1 or greater than 0, okay, the angle between U and V is less than 90, but it's basically just less than 90. We don't have to bother with saying greater than 0, because it could be 0. It's less than 90. That's all that matters. Okay. If U dot product V is equal to 0, the angle between them is equal to 90 degrees. Okay. I should also say or pi over 2. We could do this in radians, although we hardly ever do these vectors in radians. Okay. But still write it up there just in case we decide we want to. And then finally, if U dot product V is less than 0, then the angle between them is greater than 90 degrees. Okay. Alright, so that's kind of a quick and dirty way, at least you can figure out what your angle, what your relationship should be. Okay, is when you take the dot product, depending on what it is, will tell you what type of answer you should be looking for. Any questions there? Okay. So in my previous example, when I got that the dot product of the two vectors was 1, that automatically meant that the angle between them would be less than 90 degrees. They'd be acute vectors. Okay. Had it been negative, I would know they would be obtuse. They'd be greater than 90 degrees. Okay. Any questions so far there? All right. We got 5 minutes left, so let's take a look at an example of what orthogonal vectors do. Basically, examples. Okay. So a question you might get is something like, are U equaling 2 minus 3 and V equaling 6, 4 orthogonal?
Yes.
Now, why would you say yes?
Multiply both of them together.
Okay.
Multiply V1, V1, and add it to
Yeah.
V2, V2.
You quickly recognize that this thing will work out too. Also, too, if you are observant, you could generally tell when two vectors are orthogonal because the numbers they should at least be they should be different by basically the numbers should be fairly similar to give you the same sort of multiple, and one of the two should have a negative in it. Okay, or basically should have a negative in it. Or if everything's negative in one, well, the other side of one of them has to be positive. Okay, but way we quickly figure this out, we do the dot product. U dot product V would be 2 times, not square brackets, doing it back there. 2 times 6 plus 4 times minus 3. I kind of did that backwards, but those numbers should be flipped here. That gives me 12 minus 12, which is 0. It's 0, or orthogonal. Alright. Any questions there? Okay, good. So, I'm going to go ahead and let you guys go early so you can get to your next class in a timely manner because obviously with all the snow coming down.
I don't want to get